Let me start with an example that will sort of motivate where we start this problem. Let's take x to be, let's say, 60.2. Now, that would lead to the log base 1 of the number 60.2. Okay. But yeah, this is not even going to be a function. Log base 1 of 60, it's not even defined, right? If this is equal to y, okay, that would say 1 raised to the y is equal to 60.2, right? Which is ridiculous, right? But that's what this statement would say. So the range of this function is always just going to be 1, and it's not really even a function because it sends every number to, you know what I mean? It doesn't work out as a function, okay? It doesn't work out as a function. And again, where did I get this? Well, 60.2 minus 59 is 1.2, and the floor of 1.2 is just 1. So that's the input argument, and is both the input argument and the base of the logarithm is a function of x also, which makes this problem interesting. But anyway, you'll see why this makes the problem, this gives us an idea how to start the problem. Now, this is an important thing computationally. 4 is the same as 52 over 13, right? Right? And so you can see that 49 over 13 is definitely, this is what, 39 over 13? This is 39 over 13 here. So you can definitely see that 49 over 13 is between 3 and 4. And now you can see, we started at x is greater than or equal to 61 to avoid something like this right here, to avoid having 1 as the base, right? Now, let's move along. All of this follows from what I just, more or less, what I was just talking about. If x is greater than or equal to 61, in particular, if it's in this interval, which defines a floor function on that interval, when you put it in, you're just going to get b is equal to 2, okay? B is equal to 2 when you substitute any number in this interval into the floor function x minus 59, okay? Now, notice, though, that 2 to the 49 over 13 is less than 16, right? It's less than 16 because remember, this is almost 4, right? This is almost 4. So 2 to the 49 over 13 is less than 16, and it contradicts the interval that we're talking about. So we rule that out, all right? Now, in a similar fashion, we go to the next interval. We're not losing any of the integers or any of the real values here. We try 62, x between 62 and 63, inclusive on the left side. Okay, that produces a base of 3. Okay, now what you get is 3 to the 49 over 13. Now, I'm not saying this is a very tedious hand calculation. I didn't get it right. I had to check it with technology. This is a very tedious calculation to actually show the hand calculation to show that 3 to the 49 over 13 is between 62 and 63. Now, we do know this. We do know that 3 cubed is less than 3 to the 49 over 13, less than 3 to the 4th, right? So we know that much. That's trivial right there, because this is what, 27, and this is 81. Okay? So we do know our number is between 27 and 81, but that's a far cry from this. And this is a very tough hand calculation. I may never get it right. I think this is approximately 3.75. And you can do some things, but by hand, I may never in my lifetime would have gotten that right. I was getting a little bit higher up the chain, but I just didn't feel like screwing with it. So in a way, there's cheating is going on here. I do know that it's between these two numbers, and it's going to be on the high side, right? It's going to be the high side. It's going to be closer to 81 than 27 for sure, since 49 over 13 is almost equal to 4, right? So it's definitely pushing the high side. In other words, it's much closer to 81 than 27 is all I'm trying to say. But to show that it's exactly between 62 and 63, which will make it satisfy the condition and be the answer to our question. This is the answer to the question. And I didn't show the remaining work, but our next step would have been 63. And you're going to see it's just way too big. You would have 63 less than or equal to x, and I won't go through it. It's pretty clear what happens here. It's way too big. It's because the bounds are linear, more or less, and then this you're talking about an exponent, so it's really grows very fast. But so there's no solution here. In other words, this would have a floor of 4, and so you would be talking about 4 raised to the 49 over 13. Right? And crystal clear that this is way too big, right? This would be at least 4 cubed, which is 64, and it's above that, right? I mean, it's not even, this is much bigger, this is much greater than 4 cubed, right? Because remember, 39 over 13 would correspond to 4 cubed, right? So you're way out here somewhere else. You're not anywhere near being in this interval, and it gets even worse when you go to say 64 to 65. So this is, I can guarantee it's the solution, but I did have to check it with technology. The approach here is unmistakably correct, but the computation is a little beyond. I would like to know if anybody in these IMO competitions could do a computation like this, actually find integer bounds for 3 to the 49 over 13. I think it's a hard problem. There may be some tricks. I don't see how you could really do it very nicely without it being very time consuming and tedious, and error prone to boot. But anyway, the answer to the question is 3 to the 49 over 13. So let me write that down. X is equal to, it's kind of an interesting problem, it's just going to involve this exponent, but you have to find the right base, which is non-trivial. It's a little bit of work. In fact, I would have never got it by hand. I'll confess that right now. But the methodology I used, I think, is the way to go. It's just computationally, it would be a difficult competition problem. So I think that's all for today. Let's see, x equals 349 over 13. We conclusively showed that 2 to the 49 over 13 doesn't fit in the interval. It's a possibility for an answer, but it doesn't fit in the interval, which is controlled by the floor function itself. Okay? All right. That's all. Thanks for reviewing.